Welcome, everyone. Today, we are treating your Cambridge physics exam, specifically syllabus code 9702, like a high-stakes space mission. Think about it. When you're launching a rocket, there is absolutely zero margin for error. Every single calculation, every structural component, every line of code has to be totally perfect for launch. Your physics exam is exactly the same. We're diving deep into the fundamental physics of temperature, exploring how energy flows, the precise ways we measure it, and the rigorous math behind it all. But we aren't just reading facts today. We're going to look at how real students tackle these problems. You're going to meet Alex, a student who overloads their answers with raw physics facts but completely lacks analysis. And you'll meet Sam, who rushes through questions and completely misses the command word requirements. We're going to look at their flawed answers, break out the red pen, and show you exactly how to craft the perfect full-mark response. Let's get this explainer started and master the physics of temperature and heat energy together. We have an incredibly clear and structured journey ahead of us today. Think of these as our 5 mission checkpoints. We are starting with the exact meaning of temperature in Section 1. Then we'll move into Section 2, decoding the Kelvin scale. Checkpoint 3 is specific heat capacity, where we'll start applying our heavy-hitting formulas. In Section 4, we'll tackle the tricky concept of specific latent heat. And finally, Section 5, testing your knowledge, where we'll bring it all together. As we hit each of these points, I'm going to be showing you our PEAL framework. That's Point, Evidence, Explanation, Link, which is the ultimate strategy top students use to structure their physics answers. Let's build our way up from core concepts to calculating those really complex energy transfers. Section 1. The meaning of temperature. This sounds easy, right? But it's actually a surprisingly tricky question when an examiner asks you to formally define it. Let's look at exactly how net energy flow works, and more importantly, how to secure every single mark when you're asked about it. Okay, look closely at this definition. The precise word in here is absolutely crucial for your exams. Temperature is a property that tells us the direction in which there will be a net energy flow between objects in thermal contact. Now, let's talk about our student Sam. When Sam gets a question asking to find temperature, Sam rushes and just writes, "It's how hot or cold an object is, which makes heat transfer." Bam, red pen from the examiner. 0 marks. Why? Because Sam missed the most critical word in the entire syllabus for this topic, the word net. Thermal energy will always tend to flow from an object at a higher temperature to an object at a lower temperature. That is the fundamental rule dictating the direction of thermal energy traffic. But it's the net energy flow that defines the temperature relationship. You have to be precise. Before we continue, subscribe to our YouTube channel, AC Exams, at acexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Let's trace the logic of this energy flow visually, because this is exactly the kind of diagram you'll need to analyze. On the left side, we see 3 objects, A, B, and C. If energy flows from A to B, that clearly means A is at a higher temperature than B. And if energy flows from B to C, then B is at a higher temperature than C. Therefore, using basic deduction, we can logically conclude that energy will definitely flow from A to C, because A is at a higher temperature than C. But now, look at the right side of the visual. We have objects P, Q, and R. The diagram shows absolutely no net energy flow from P to Q. This means they are at the exact same temperature. They have achieved what we call thermal equilibrium. Now, let's talk about our other student, Alex. Alex would write a massive paragraph here about the kinetic energy of the particles vibrating in P and Q. But the command word just asked to state the condition of P and Q. Alex wasted 5 minutes writing a novel and got no extra marks. The perfect, concise answer: if there is no net energy flow from P to Q, they are in thermal equilibrium. Furthermore, if there is no net energy flow from Q to R, they are also in thermal equilibrium. Consequently, there will be no net energy flow from P to R. The ultimate takeaway here is that when there is 0 net energy transfer between objects in thermal contact, they share the exact same temperature. Moving right along to Section 2, the Kelvin scale. Now that we thoroughly understand that temperature dictates energy flow, let's explore how we actually measure it, and how Cambridge expects you to differentiate between everyday measurements and thermodynamic scales. To measure temperature in the real world, we have to rely on the physical properties of materials that change in a highly predictable way as things heat up or cool down. Think of a past paper question that says, state 3 physical properties that can be used to measure temperature. If Sam is taking this exam, Sam might write, liquids get bigger, metals get hot, and gases change. Again, the examiner brings out the red pen. You need specific scientific language. We can use the expansion of a liquid, which results in a change in density. We can measure the change of pressure of a gas at a constant volume. Moving into the electronic side, we can measure the change in electrical resistance of a metal or a semiconductor, or we can measure the electromotive force, the EMF, produced across the junctions of a thermocouple. All of these are incredibly valid, practical ways to measure temperature changes, but notice the flaw here. They all rely on the specific, sometimes quirky behavior of a particular material. What if we want a scale that is universally true, no matter the substance? That's exactly where the thermodynamic temperature scale, also known as the Kelvin scale, comes into play. It is completely independent of the physical properties of any particular substance. It is built upon a theoretical, absolute baseline, absolute zero. Let me break this down using our PEL framework. Your point is that absolute zero is the temperature at which no more energy can possibly be removed from an object. Your explanation is that all the energy that can be removed has been removed. At this exact point, all substances have their absolute minimum internal energy. Now, it's totally vital to note, and this is a classic exam trap, that this does not mean the object has absolutely zero energy. Only a theoretical ideal gas would have zero energy and zero pressure at this point. In the real world, absolute zero is equivalent to exactly minus 273.15 degrees Celsius. Let's look at how we apply this in practical calculations, because this conversion trips up so many students. Converting between the Celsius scale and the Kelvin scale is actually incredibly straightforward. Temperature in Kelvin equals the temperature in Celsius plus 273.15. Let's walk through a few examples. The boiling point of pure water at standard atmospheric pressure is 100 degrees Celsius. To find that in Kelvin, we simply add 273, giving us 373 Kelvin. Because the boiling point of water is typically given only to the nearest degree Celsius, simplifying the conversion by just adding 273 instead of 273.15 is perfectly justified in most of your practical exam calculations. Take the boiling point of helium. It's an incredibly cold 4.37 Kelvin. To find the Celsius equivalent, we just do the reverse and subtract 273.15, revealing a freezing temperature of minus 268.78 degrees Celsius. Mastering this simple conversion is a baseline skill you must have locked down before stepping into that exam hall. Let's move into our third section, specific heat capacity. This is where we see a major transformation in how you handle multi-step math problems. We're going to look at exactly what happens when we continuously supply energy to a material. When an object is heated, its temperature obviously increases, but the specific amount that its temperature increases, which we call delta theta, depends on three distinct factors. It depends on the amount of energy supplied, which is delta Q. It depends on the mass of the object, m, and it depends entirely on the specific material the object is actually made from. This relationship is perfectly captured in the equation delta Q equals m times c times delta theta. The c in this equation is our constant of proportionality, known as the specific heat capacity of the material. If we rearrange the formula, we find that c equals delta Q divided by the product of mass and change in temperature. Therefore, the formal definition of specific heat capacity is the energy required to raise the temperature of a unit mass of a material by 1 unit of temperature. The standard units here are joules per kilogram per Kelvin. And remember, because the size of 1 degree Celsius is geometrically identical to the size of 1 Kelvin, saying joules per kilogram per degree Celsius is numerically exactly the same thing. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, we are going to see this specific heat capacity formula in action with a classic high-mark scenario, the electric shower problem. I'm going to show you how our student Alex completely overcomplicates this and how you can do it perfectly. We have an electric shower working from a 230-volt main supply. Water enters the heater at 12 degrees Celsius and leaves at 28 degrees Celsius, giving us a temperature change of 16 degrees. The mass flow rate is 0.12 kilograms per second. We need to calculate the electrical current drawn by the heater. Alex sees this and panics because there is no total time given. Alex tries to invent a time variable, messes up the algebra, and loses all the marks. Here is your success blueprint. Step 1, identify your knowns. Step 2, set up your power equation. We must balance the electrical power input with the thermal power absorbed. Electrical power is voltage times current, V times I. Thermal power, since we have a mass flow rate per second, is simply mass per second times C times delta theta. So V times I equals M times C times delta theta. Step 3, substitute confidently. 230 volts times our unknown current I equals our mass flow rate of 0.12, multiplied by water specific heat capacity of 4,200, multiplied by our temperature change of 16.
Step 4. Solve. The right side becomes 8,064 watts of thermal power. Divide that by 230 volts, and boom, we get a current of exactly 35 amps. Perfect marks.
Welcome to Section 4, Specific Latent Heat. We're now shifting into our interactive workshop phase. What happens when water reaches its boiling point of 100 degrees Celsius and just stays there, even though we keep adding tons of energy? This is your first challenge. We're doing a find the flaw exercise. Look at the definitions on screen. We are dealing with latent heat, energy doing the actual work of separating molecules to change the state of the material rather than increasing its kinetic temperature. We have the specific latent heat of fusion, which is the energy required to change a unit mass of a solid to a liquid with zero temperature change. And we have the specific latent heat of vaporization, changing a liquid to a vapor with no temperature change. If Sam wrote on an exam, latent heat is the energy needed to melt a solid into a liquid. Can you spot the flaw? Sam is losing marks right there. Sam forgot two absolutely crucial elements, unit mass and no temperature change. In Cambridge physics, missing those qualifiers drops you from an A to a B instantly. You must specify that it is per unit mass, and you must explicitly state that the temperature remains completely constant while the state change occurs. Whether we are melting solid ice into liquid water or boiling liquid water into steam, the mathematics are governed by one incredibly elegant equation. L equals delta Q divided by delta M. Here, L represents the specific latent heat. Delta Q is the total thermal energy input. And critically, pay close attention here because this is your speed writing challenge, delta M is the mass of the substance that has actually changed state. It is not the total mass of the object sitting in the beaker. It's just the mass that was successfully converted. I want you to mentally draft a PL paragraph right now explaining why we use delta M instead of just M. Got it? Good. It's because the energy is only consumed by the molecules that are actively breaking their intermolecular bonds. Time for challenge number 2, the data scan. You have 60 seconds to visually process this practical lab setup. In a real exam, you might be asked to describe an experiment to measure the specific latent heat of fusion of ice. Look at the apparatus. We have a power supply connected directly to a heater embedded in a funnel of melting ice. Below that funnel, a beaker catches the liquid water, and this beaker sits precisely on an electronic balance. How do we extract the core trend here? By measuring the electrical power input to the heater over a specific time, we calculate our total energy supplied, our delta Q. By tracking the exact change in reading on the electronic balance over that exact same time period, we isolate our delta M. That's the mass of the ice that has successfully melted. By dividing the electrical energy by the change in mass, we experimentally derive the specific latent heat. If you can explain that process clearly, you've just bagged a guaranteed 6 marks. Let's tackle the final boss calculation of this segment. Imagine a 1.5 kilowatt kettle containing 400 grams of already boiling water. It's left switched on for an additional 5 minutes. We need to calculate the exact mass of water remaining in the kettle. Here is exactly how you decode this. Step 1. Time must always be in seconds. 5 minutes is 300 seconds. Step 2. Calculate the energy, delta Q. Power is energy over time, so energy is power times time. 1.5 kilowatts is 1,500 watts. Multiply that by 300 seconds, and we get 450,000 joules of energy. Step 3. Rearrange our formula to solve for mass. Delta M equals delta Q divided by L. So our 450,000 joules divided by the specific latent heat of 2.26 million joules per kilogram. This gives us a vaporized mass of 0.199 kilograms or 199 grams. Now, here is the absolute classic mistake. Sam gets to 199 grams, double underlines it, and moves to the next page. But Sam didn't read the command requirement. Step 4 is the crucial trap. The scenario asks for the mass remaining. We started with 400 grams. We boiled away 199 grams. Therefore, the remaining mass is exactly 201 grams. Always, always reread the final sentence of the question. We've reached Section 5, testing your knowledge. Let's wrap up our explainer today, review the core concepts, and solidify the strategies you need to apply these thermodynamic principles flawlessly in your exams. Take a screenshot of this checklist right now. This is your ultimate revision tool to ensure you've mastered the concept of net energy flow, the thermodynamic Kelvin scale, and the formulas for specific heat and latent heat. But beyond the formulas, I want you to remember the complete physics answering system we used today. Rule 1, command word decoding. Always identify if they want a state, a define, or calculate. Rule 2, Peel framework application. Structure those longer written answers logically.
Rule 3, time management matrix. Don't waste 10 minutes writing a kinetic energy novel for a 2-mark question like Alex did. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
I'll leave you with this absolutely massive, planetary scale calculation to ponder. Based on the latent heat of fusion we just learned, how much of Earth's ice would physically melt if our atmosphere retained just 0.1% more solar energy instead of re-radiating it into space? This shows that the physics you are learning isn't just for an exam paper, it literally dictates the balance of our entire planet's ecosystem. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.